Alright everyone, welcome back. Today we are talking about buoyancy. What is buoyancy? Well, I think this is a good depiction of it over here. We see this cork over here. It's feeling a lot of buoyancy. Why isn't it falling down due to gravity? Because buoyancy is keeping it up. Okay, but there is also buoyancy acting on this, but it's not as noticeable. And we'll talk more about this. Alright, so let's move on. Buoyancy is the net upward force that is exerted on objects submerged in a fluid. The object is pushed upwards due to greater pressure at the bottom caused by its depth in the fluid. Okay, so you notice this whenever you're in like a pool or something like that. You feel lighter. You feel you can jump higher. Any kind of fluid, honestly, there's this force of buoyancy that's going to be pushing you upward. Okay. Sometimes it's more than gravity, sometimes it's less than gravity, and it depends. Okay, so here we go. Understanding buoyancy. So when an object is in water, there are primarily two forces acting on the object, the force of gravity and the force of buoyancy. Depending on the object's density and location in the fluid, gravity and buoyancy can be unequal or equal. Okay, so in this situation, it's not accelerating downwards or accelerating upwards. There's no acceleration. So the buoyancy and force of buoyancy and force of gravity are equal. However, let's say it's completely submerged, it sinks all the way down, the gravity is stronger than the buoyancy. Okay. Another thing is maybe someone pushed it down and now it's going upwards. The force of buoyancy would be more than the force of gravity. For example, if you pushed a balloon into the water, okay, the force of buoyancy would be more than the force of gravity. Okay, just some examples. Alright, so let's look at this. First conceptual example. A rubber ducky is not moving while floating on the water. In this case, which force is greater on the duck? The force of gravity or the force of buoyancy? Alright, again, pause it whenever you want to just do it on your own. It's really important. But here we go. The answer is going to be they're both the same. So, same thing. There's no acceleration on this, so that means all the forces acting on it have to be equal to 0. And there are only two forces acting on it, force of gravity and force of buoyancy. Okay. Moving on. A rubber ducky was initially floating in the pool, but a child submerges it underwater. In this case, which force is greater on the duck, the force of gravity or the force of buoyancy? This is a bit trickier, okay? But while it's in the water like this, let's think about what's going to happen. This rubber ducky is going to start to rush back up to the surface of the water. So right now we have a certain amount of force of gravity, but since it's going to be rushing up and it's going to be accelerating up here, there's going to be a force of buoyancy that's a lot stronger before it gets onto the top of the water. Okay, so the force of buoyancy will be more at this current position. Okay. A rock is thrown into water and sinks. Which force is greater on the rock while submerged? Gravity or buoyancy? So this sinking just kind of shows that, that the force of gravity is more than the force of buoyancy. Okay, so it's going to be the force of gravity. Okay, and if that wasn't the case, it wouldn't sink. Okay, it would be floating up there. All right, moving on. So this is the Archimedes Principle. It's a pretty interesting principle and demonstration. Archimedes' Principle states that the buoyant force on an object is equal to the force of gravity of the fluid it displaces. Okay, so this is a little bit interesting. Okay, so we know that density is equal to mass divided by volume. Mass is also, if we do the algebraic manipulation, mass is equal to density divided by volume. So, if we look at, let's say for example, we're going to just take this bit of water right here. Okay, we take that bit of water. This bit of water has a certain amount of mass and gravity going to be acting on it. And then that would be giving us the density times the volume times gravity, okay? And that's what the force of buoyancy is going to be telling us. The force of buoyancy of any object is going to be equal to the mass of that water displaces. So let's say we have a ball like this, same shape. It's going to be whatever this mass is of the water times gravity times the density of it. So in this case, we're talking about water. So if this rock has more mass than this displaced water right here, it will sink. However, if this ball over here has less mass than this ball of water over here, then it'll rise to the top. Okay, so that's kind of how buoyancy is described. There's also there's a formula derivation of this, so you can look at that if you want to look at that. Another thing that's important to know is, for example, we have this 5 kilogram weight here, and in the air it's 5 kilograms, as you can see. But once we put in water, we know it's not going to be as much because of buoyancy. So once it goes up, we can see it's only 3 kilograms now. So what happens to the other 2 kilograms? Well, if this is full, that means it'll fall out. 2 kilograms of water will fall out. Okay? And if a little demonstration of this, I'll show that. So this is me doing a demonstration. I'm going to put it on silent so that I can kind of explain as this is going on. So let me also go fast. Okay, so I have this kind of cup over here that's 0.2, I think pounds. Yeah, 0.2 pounds. As you're going to be noticing. Okay, 0.2 pounds. And then I have this rock over here that's 0.56 pounds. As you can see over here, 0.56. And then I'm filling up this water to the tippity top. Okay, so I'm filling it up as much as possible. And then what I'm going to do is I'm going to put that rock inside of it, and you're going to notice as I put it onto it, it's going to get lighter because it's in the water. The force of buoyancy is going to be acting on it, so in the water it feels lighter, the rock. And whatever it's going to be lighter, okay, let me go move on, then it's going to displace a certain amount of water. So we can see it's getting lighter. So it's less, and it's around 0.37. So it was 0.56 originally, so it went down around 0.19 pounds. Okay, so that means that 0.19 pounds should be inside this cup right here. Okay, so what I'm going to be doing now, since it's displaced 0.19, now we're going to be weighing this. And this 0.2 should now be up to 0.39. So 0.2 plus 0.19, so it should be 0.39. So let's see what happens. Okay, it's around 0.4, but then it balances 0.39. Okay? So a little bit of the Archimedes Principle, how it all works, a little bit about buoyancy and everything like that. Okay, so let's do some examples, and as we do examples, it's going to make more and more sense. A rock has a weight of 10 newtons on land, but its weight submerged in water is 6 newtons. What is the force of buoyancy on this rock? Okay, so it's kind of I guess it's kind of like interesting. Okay, so what we're going to be doing here is we have a rock, right? In the air, there's this force of gravity that is equal to 10 newtons. However, in the water, this rock over here has a force of gravity, which is actually still equal to 10 newtons. However, what's happening here is there's an upward force acting on it where it only feels like it's around 6 newtons. So if that's the case, if it's feeling like 6 newtons, that means there's going to be an upward force over here, the force of buoyancy, which is going to be equal to 4 newtons. And that's why it feels like there's only the net force is equal to 6 newtons. Okay? Hope that makes sense. Okay? Your weight doesn't change. It's just that there's an upward force on you now that makes it feel like there's less weight. Okay, so the net force does change. Okay, moving on. A 40 kilogram cube is floating in the water. Density of water is 1,000 kilograms per meter cube. What is the force of buoyancy acting on this cube? What is the volume of water this cube has displaced? Okay, so first thing that we should know is this thing over here, this cube, the net force is equal to 0. How do we know net force is equal to 0? Because it's just floating on the water. So there's a force of gravity and there's a force of buoyancy. Okay, and if the net force is equal to 0, that means they have to cancel out with each other. So force of gravity is just 40 times 10, so that's 400 newton. And that means the force of buoyancy is also going to be 400 newtons. Okay, so a little bit more confusing here. Part B is, what is the volume of water this cube has displaced? Okay, so we know when this comes in, the water level is going to rise, and we kind of want to know what's the volume of it rising, I guess, in this situation. So we're going to go back a bit and we're going to look at the formula over here. We can see that the force of buoyancy is equal to the density times the volume times gravity. Okay, so we're going back over here. So we know force of buoyancy is equal to density, volume, and gravity. Force of buoyancy, we know it's 400. Density is equal to 1,000. Volume is what we're looking for, and gravity is 10. Okay, so let's put this into our calculator. 400 divided by 1,000 divided by 10, and we should get 0.04 meter cubed. Okay. Oh, volume of the water. Sorry, that should be cubed. Okay, example number 10. A cube is floating in the water. The cube's length, width, and height is equal to 0.8 meters. Half the cube is submerged underwater. Density of the water is 1,000 kilogram meter cubed. What is the force of buoyancy acting on the water? Okay, so a few things to know here. This part here is going to be half of 0.8 meters. So this is 0.8 meters here. And then what we should also know is, oh, maybe I'll do this in a different color. Do this purple here. This is a three-dimensional object, right? Yeah, and like this, and like this. Okay, so we should know that this length here, oh sorry, this isn't 0.8, this is 0.4, this is 0.8, and this is 0.8. Okay, so first, if we're going to try to find the volume, we know that's going to be 0.4 times 0.8 times 0.8. So let's see what that is equal to. 0.4 times 0.8 times 0.8, and we get 0.256 meters cubed. Okay. Next thing we should know is density is equal to mass divided by volume. We know density is 1,000. The mass is what we're looking for. We're looking for the mass of the water of this section of the water that it's going to be consuming. The volume is 0.256, and we get mass is equal to 256 kilograms. So we know that this cube displaces 256 kilograms of the water. So now we should know that the force of gravity of this water is equal to the force of buoyancy. So that's just 256 times 10, and then we get 2,560 newtons. All right, hope that makes sense. A rock that has a mass of 5 kilograms is sinking underwater. The rock has a volume of 0.0008 meters cubed. What is the net force acting on the rock? It's sinking underwater. Okay, great. So let's see. What we're going to first do now is we have the density of the water is equal to the mass of the water divided by the volume of the water. Okay, so we know the density of the water, 1,000. Mass of the water, we don't know what that is, so we're going to look for that. And then the volume of the water, we know it's going to be displaced 0.0008 meters cubed. So let's find this mass of the water first. 1000 times 0.0008. And we have 0.8 kilograms that it displaces. So this is also going to tell us that the force of the buoyancy slash the force of gravity of the water it displaces is equal to 0.8 times 10, so 8 newtons. Okay, so that's the amount of water that's displaced. So as this rock falls, we know that the force of gravity is equal to 5 times 10, which is 50 newtons. And we also know that the force of buoyancy is going to be equal to 8 newtons. So what's the net force going to be equal to? It's going to be equal to, I guess, downwards 42 newtons or negative 42 newtons. Okay, but it's going to have a magnitude of 42 newtons. Okay. All right, moving on. This is a good video that shows a bit about it. I can't show it here because I didn't make it, but I suggest watching it. Okay, now let's look at this. Rank the densities of the 3 objects which have reached equilibrium from least to greatest. Please refer to the diagram below. Okay, so pause if you need to, but here's the answer. We have A, B, C. And we should know that this is the least buoyant because it is floating. The second one over here, if it's floating kind of in the water, what that means is the buoyancy is exactly the same. So this has the same exact density of water or whatever this fluid is. And since this one has sunk to the ground, that means that it is more dense than the water. Okay. If an object is fully submerged in water but is also not sinking nor moving up, what do we know about the density of this object? Okay, so we just talked about this, so this should be C. Its density is equal to water. Okay, moving on. 3 objects are completely submerged in water and have the same mass but different densities. Object A has a density of 12,000 kilograms per meter cubed. Object B has a density of 11,000 kilograms per meter cubed. And object C has a density of 10,000 kilograms per meter cubed. Which object experiences the greatest force of buoyancy? Okay. So this is an interesting question. Take some time. How this is going to work is the answer is C here. And again, if you want to pause it to think why, the answer to C here is, and that's because C occupies the most amount of volume. And since it displaces the most amount of water, remember buoyancy is dependent upon how much water is displaced, and that's why since it displaces the most amount of water, it's going to have the most amount of force of buoyancy. Okay, the mass of that water will be the most, and mass times gravity is also equal. Mass of the water times gravity is equal to the force of buoyancy. Okay, moving on. A cork that has a density of 200 kilograms per meter cubed is attached to a string and submerged in water. The volume of the cork, is 0.018 meter cubed. What is the magnitude of the tension in the string? Okay, so a few forces here, so let's kind of draw it out. We have the force of gravity. We have the force of tension. And then we have the force of buoyancy. Alright, so a lot to kind of unpack here. So cork, the volume of the cork. Okay, so let's do density of cork is equal to mass of cork divided by volume of cork. So density of cork is 200, mass of cork we don't know, volume of cork is 0.018. So the mass of the cork, let's figure that out. 200 times 0.018 is going to be 3.6 kilograms. Pretty big cork. Okay. Next is, okay, so now that we know that, we could figure out what the force of gravity is. 3.6 times 10, 36 newtons. Okay, now let's figure out what this force of buoyancy is. So we should know that the density of water is equal to mass of water divided by volume of water. Density of water is 1,000. Mass of water we do not know yet. Volume of water is equal to, well, it's displaced the same amount, 0.018. So now we can find the mass of water, which is 1000 times 0.018, and we get 18 kilograms. Okay, so a good amount of water displaced. And we should know that the force of buoyancy is just the force of gravity of that, so that's going to be 180 newtons. Okay, so now just looking at this free body diagram, we could just do the sum of all force in the y equals mass times acceleration in the y. Force of buoyancy on top minus force of gravity minus force of tension is equal to 0 because it's not moving. Force of buoyancy 180 minus 36 minus Ft equal to 0. The force of tension is going to be 180 minus 36. It's going to be negative 144, but it's asking for the magnitude, so we're just going to put 144 newtons. Okay. All right, guys. Hope that all made sense. Hope that was good for you guys. Next time, we're going to finally be talking about fluid dynamics. See you for that one. Bye.